In chemistry, we represent chemical reactions by writing out the chemical formulas. And this is a shorthand, kind of like when you're writing sentences in English. So we have the words, which are our compounds, and we have our sentences, which are our chemical equations. Now, our chemical equations have specific rules, and one of those rules is that it has to follow the law of conservation of mass, which means that we are not creating or destroying matter. And so the elements on the left-hand side of the arrow in our chemical reaction have to be the same number and type as the ones that are on the right-hand side, or the products of our reaction. We cannot make new elements, and we cannot lose elements in our chemical reaction. There are different parts when we're looking at our chemical reaction. So the reactants are the things in the red box on the left-hand side of the arrow. Those are what we're starting with, or our starting materials for the chemical reaction. The products are on the right side of the arrow. That's what we end up with. And so those are represented by the blue box in our reaction shown on the slide. In order to balance these chemical reactions, we have to change the coefficients in front of the compounds. So we are not allowed to change subscripts, because that would change the compound, but we can change the numbers in front of each of the compounds, which is the coefficients. And so in order to balance it, we make sure that we have the same number and type of atoms on both sides of the chemical reaction. So in our example, by putting a 2 in front of our hydrogen, this tells us for hydrogen, we have 2 times 2 for a total of 4 hydrogen on the reactant side, and we have 2 times 2, so 2 times 2 for a total of 4 hydrogen on the product side. For our oxygen, there are 2 oxygen on the reactant side, and on the product side we have 2 times 1. If there's no subscript written, we assume it's 1, and so there's 2 oxygen. So this particular example is balanced because we have the same amount and type of elements on each side. So when we balance our chemical reaction, we are only allowed to change coefficients. In this chemical reaction, we say that we've got 2 hydrogen and an oxygen that produces 2 water molecules. Now this is a very different chemical reaction than one where we change the subscript. If we change the subscript, now we say that we've got hydrogen plus oxygen produces hydrogen peroxide, and hydrogen peroxide is a very different compound. It's highly reactive, and this is a compound that in very dilute quantities you may have used to clean out wounds when you were a child, and you see it bubble and fizz because it's highly reactive. So we're only allowed to change coefficients, not the subscripts. So when we're balancing them, we have some guidelines that we can follow to make it a little bit easier. So if an element only occurs in one compound, it's a good place to start by balancing that compound or that element first. If an element occurs all by itself as a free element with nothing else attached to it, we leave that one to last, because if we change the number in front of that, it doesn't change anything else in the chemical reaction. We can only change coefficients, never subscripts. And we want to eliminate fractions. It has to be the lowest whole number ratio for our coefficients. So you will not see fractions in front of our balanced chemical reaction. So again, these are guidelines, not rules, but it does help you to balance the reactions a little more efficiently. And these actually probably would be rules because we cannot change the coefficients and it does have to be whole number ratio. So let's practice. Let's balance the following chemical equations. If you're looking for more practice, this is a helpful website that you can go to gain some more additional practice. So I typically start with the more complicated compound. So in this case, it would be the aluminum oxide. I can see that there's one aluminum on the right side. There's one aluminum on the left. Okay, so the other thing I see is that there's 3 oxygen. So the 3 oxygen and there's 2 on the right. So our lowest common multiple is 6. So if we put a 2 in front, that means that we'll have 6 oxygen. And for our oxygen on the left-hand side, we've got 2. So if we multiply by 3, that will give us 6. That will allow our oxygens to be balanced. But now we have to look back at the aluminum because we've changed the coefficient. We've got 2 aluminum. So if we put a 2, then our chemical reaction is balanced. Okay, so on our chemical reaction, we've got an odd number of oxygen on the right and an even number of oxygen on the left. So I'm going to start by putting a coefficient of 2 in front of our SO3. That gives me 6. It also changes the amount of sulfur. So if we look at the sulfur, we've got 2 sulfur on the right. So that means we're going to have to put 2 sulfur on the left. Now that our sulfur is balanced, let's check our oxygen. So we've got 6 on the right. We've got 2 times 2 for our sulfur dioxide, which is 4, plus 2, which is 6. So just by putting that 2 in front of the 2 sulfur containing compounds, it allowed us to balance our reaction. This does take a little bit of practice, and so if this isn't coming very quickly to you, don't feel bad. It takes a little practice to see these things. All right, so here's another example, and I want to show you, so sulfate is the same on both sides of the chemical reaction, and so I'm going to balance it as one complete unit. So I don't worry about balancing each element individually because it's SO4 on both sides. You can kind of think of it like a big X. So because there's 3 of them on the right side, I know I need 3 of them on the left side. We've got 2 iron on the right side. We'll put 2 in front of the iron on the left. Now let's look at our hydrogen because everything else is balanced. But our hydrogen, we've got 3 times 2, which is 6 on the on the left side. So 3 times 2, which is 6. So in order to balance our hydrogen on the right side, to get 6, we need to put a 3 in front of the hydrogen. The very best part about balancing chemical reactions is you know that you've done it properly when you check to see that all of the elements balance. Here's one for you to try. See if you can balance these 3 chemical reactions. Pause the video and balance the reactions. Let's look at our aluminum reaction. So I'm going to start with the more complicated species, which is our aluminum sulfate. I see that I have 3 sulfates, so I'm going to go to the right side and add a 3 to balance the sulfate. I see I have 2 aluminum on the left side, so I'm going to go to the right side and put a 2 to balance the aluminum. Now let's double check. So for our calcium, on the right side we have 3, and on the left side we just have 1. So I'm going to put a 3 in front of the calcium. By putting that 3, that means I have 6 hydroxides. 3 times 2 gives me a total of 6. If I look on the right side, I have 2 times 3 for a total of 6. Let's look at our next one. This is a special type of chemical reaction, and this is called a combustion reaction. So for combustion reactions, we balance them in a very similar way. So we can see that we've got 2 carbon on the left. So I'm going to try 2 carbon on the right. I've got 6 hydrogen. So to make 6, because there's 2 hydrogen there, I need to put 3 in front of it to get a total of 6. Now what this does is it gives me, on the right hand side, 4 oxygen and 3 oxygen for a total of 7. Okay. So in order to balance the oxygen, we actually need, because there's a 2 here, it's diatomic, we are going to need 3.5, which we can also write as 7/2 oxygen. Okay, now we're not allowed to have fractions, but we can get rid of fractions pretty easily. So if we take and we multiply each of those coefficients by 2, we end up with 2C2H6 plus 7O2 yields 6H2O plus 4CO2. Now because we multiplied the entire reaction, it doesn't change our balancing, but it does change it so that we don't have that fraction. And so this is a way that we can balance this chemical reaction. If we go to the next one, we've got C4H8. So for our carbon, we're going to need 4 carbon. For our hydrogen, to make 8, we need 4 times 2 to get 8. Now for our oxygen, we have 4 times 2 from the carbon dioxide, so 8. 4 times 1, 4, so we've got 12. So in front of our oxygen, in order to make 12, we have 2, so we put 6. So this time we didn't need a fraction because we had an even number of oxygen on the right-hand side. So how do we read this chemical reaction? So we can say that we've got 2 molecules of hydrogen plus 2 molecules of oxygen to make 2 molecules of water. We can also read this in a different way. We can say that we've got 2 moles of hydrogen that reacts with 1 mole of oxygen to make 2 moles of water. So a mole is a chemical quantity, and that quantity is equal to 6.02 times 10 to the 23rd. Really, it can be anything, but we usually use it for very small quantities like molecules or atoms. And the reason that we use moles is because this puts the reaction into amounts that are much more reasonable to handle in a chemical laboratory. And so it's much easier to weigh out a mole of substance as opposed to we cannot handle just a couple molecules at a time. They're way too tiny. So just to put things kind of in perspective and explain what a mole is. So a mole of graphite, a mole of anything, a mole of graphite contains 6.02 times 10 to the 23rd atoms of carbon. So this would be about 12 grams of carbon. So to put that in perspective, a dollar bill weighs about a gram. So if you had $12 bills worth of pencil lead, $12 bills of weight of pencil lead, that would be 1 mole, which doesn't seem like much. But if we had a mole of sheets of paper and we stacked one on top of each other, it would reach outside of our solar system. So when we get into much larger quantities, this is a huge number. 6 with 0.02 with 21 zeros behind it. 1 mole of basketballs, it would create a planet about the size of Earth. If we had 1 mole of rice, it would cover all of the land on Earth 75 meters deep. Okay, so just think about how big the mole is and how tiny our molecules are, that such a small amount can be easily manipulated or handled in the lab. If you had a mole of pennies, this is my favorite one, mole of pennies, and you gave away $1 million of it a day, to everyone in the world, it would take you more than 3,000 years to distribute all of your money. But if we look at water molecules, if you had 18 milliliters of water, about 3.5 tablespoons, okay, that is 1 mole of water molecules.